Welcome to this quick overview of the ANSYS Fluent graphical user interface. So this will be a very brief introduction intended for people without prior Fluent knowledge. I will quickly set up a case and illustrate a few common post-processing options. So let's begin. Here we have the Fluent graphical user interface. And if you come from Workbench, then your mesh is imported directly from ANSYS Meshing. In this particular case, I have created the mesh in the open source software called Salome, and then read it into Fluent. We can begin by looking at the mesh if it's not automatically displayed. So as you can see, it's a simple tetrahedral mesh of a cylinder. And the second thing to do is to make sure that the scale is correct. Here you can see we have a very large model, so this was actually created in millimeters. So we set millimeters and hit the scale. I recommend to always create your models in meters when possible. This will help avoiding simple mistakes. Now let us check the mesh and see if any problems are detected. No warning is issued here, so everything appears to be fine. And then we can continue. And now it's good to report the quality of the mesh. And the key quality indicator to look for here is the minimum orthogonal quality. And you can see it's 0.1 approximately. And the orthogonal quality should be as close to 1 as possible. With curved boundaries, it's a bit difficult to achieve this. And we can try to improve the mesh using whatever meshing tool we have. Another option is to convert this tetrahedral mesh to polyhedra. We can do it by just clicking this button, make polyhedra. And then let's display it again. And now you see it just disappeared, and that's some weird bug in this software. So we can go into view, go into views and hit the default view again. So now we have it back again. So now you can see that we have converted it to a nice honeycomb polyhedral mesh structure. So let's check the mesh again and see if we have any warnings, and it appears to be okay. So finally, let's report the quality, and yeah, now you can see that the minimum orthogonal quality has improved by a factor of 2 to 3. Okay, for this case, we will be using a steady state pressure-based solver. So when I go through this in general, if there is an option you do not understand, just leave it at the default value. So having a look at the models task page, here's the task page. We can set different options for multiphase, energy and viscous model. At this time we will not use any particular models, which means that we have an isothermal laminar flow. If we hit edit in the materials task page here, we can look at the physical properties of the fluid under consideration. And now we have air, and you can see that the density is constant, which is fine considering we will use low velocities for this case. However, if we solve the energy equation, we could model compressible flow using, for instance, the ideal gas law here as the equation of state. So we leave everything at the default values, and if we go into cell zone conditions, it is possible now to specify the operating conditions. Most simulations have a reference pressure, and here you can specify the magnitude and also the location. We will not use gravity, but it can also be specified here in whatever direction we want. So now we come to the most important task page, and that's the boundary conditions. If the mesh comes directly from Workbench, then all boundary condition names will be translated to appropriate boundary conditions. And if you hit here, you can look at the type. Since I have used Salome to generate the mesh, all boundary conditions have been set to pressure outlet, as you see. So let's change the inlet to velocity inlet, and then we set 1 meter per second normal to the boundary as a boundary condition. Then we change the wall from pressure outlet to wall, and you can see that now we have a stationary wall with no slip. And the pressure outlet we can just leave as pressure outlet. So let's go to the methods, and here we can leave everything at default values except for this checkbox with pseudo transient, and we uncheck that box. When we are finished with this, we can go into initialization to initialize the solution, and the standard, the default option here is the hybrid initialization. And this will try to guess a good starting value to reduce the computational time. We can also do it manually by using this standard initialization. And here you see that we guess that we have a starting condition of 0 of all the relevant variables. Since the inlet velocity is 1 meter per second and we only have a straight pipe, it is reasonable to initialize the domain with that velocity. So let's put 1 here, and then we hit initialize. So now we have 1 meters per second in the z direction everywhere in the domain. Now we need to go in and specify the residuals. We can do that. We go in, expand the monitors here and go into residuals. Usually what I do is I uncheck this plot window and I accept that we only can read the residuals from the console output. You can see that the residuals are set to 1e minus 3. It may be a bit too high for a steady state solution. However, for transient solutions it may be sufficient if the time step is small. So we leave the defaults as is for this particular demonstration. So now if we go into run calculation, we can set the number of iterations. So we put some number here, 1000. And this is the maximum number of iterations that Fluent will take during this simulation. So the simulation will stop as soon as it reaches the convergence criteria that we specified here on the residuals. If your solution reaches the number of iterations set here, then it have not converged. So the convergence criteria for some of the variables might be off, and therefore you should be very careful when interpreting the results. We can also do a check case here, and we have no recommendations to make at this time, which seems that we have set everything up properly. So hit calculate. Okay, now it says that it must be initialized and before it can be started. Let's see if we perhaps forgot to push the button here, initialize. So do that and then hit calculate. So you see after 40 iterations it converged. So we see that all the relevant residuals are below 1e minus 3. And you see now that the number of iterations we set to 1000, we only needed 40. So now that we have a converged solution, we can go to the graphics task page and look at the results. So if we go into contours and then display the pressure field, and we need to set what surface we can display this on, and let's use the wall here. So here we can see the pressure field on the wall. We can make it more interesting and create a surface. So let's create an isosurface, just a cut plane through this three-dimensional cylinder. So then we go into surface of constant mesh, and then we just pick the x-coordinate and create that. Then it creates a new surface called x-coordinate 4. So if we pick that one, we can plot the velocity over that new surface. So this is the velocity profile that we have, and when looking at this velocity profile, now perhaps it's time to consider what actual Reynolds numbers we have used in this case. Preferably you do that before you run the simulation, but I think this is a good showcase. So the question is this really laminar in this flow case? Well, if we expect turbulence, then we need to use a turbulence model, especially considering the very coarse mesh we do have here. So instead of using a turbulence model with this high Reynolds flow, let's change some material properties and see if we can make this a low Reynolds flow. So let's change the viscosity by a number of order of magnitudes. So now we have some new material. Let's call it air, doesn't matter. Then we can initialize and run the simulation again. It's okay to discard the previous solution. And then we run the simulation. Now it converges in 26 iterations. So let's go and see if the contours have changed in any way now. So now we have a much more reasonable flow profile. It has changed a lot. So, you know, in fluid mechanics textbooks, we normally see that the velocity profile in a pipe is parabolic. And here it may be difficult to directly see this, considering this is a contour plot, although we can understand it, that we see that the velocity is higher and uniform at the inlet, and then it changes to a high velocity in the center and lower velocity at the walls. Anyhow, let's try and see if we can create an XY plot. So we can look at this parabolic profile. Now I suggest that we do a new surface. Let's create a line at the outlet plane. Let's see, we had 0.3 in Z direction. That's the maximum height. And then it's negative 0.1 to 0.1. So now we have created a line called line 5 here. So now we can go in and plot the velocity magnitude along the curve length of line 5. So here you have it. You can see that we have the parabolic velocity profile, similar to the textbook examples. So this concludes this short introduction to the ANSYS Fluent graphical user interface.